Hello, everyone. Thank you so much, Confer Conf, for having me as a speaker. It's actually my first time I do a speech for an innovation conference, so that's one thing I can brush off my bucket list. And for the watchers that are registered to see this conference, so welcome. I hope I can add some value to you. And as you already know, we are going to talk about something called robustness, machine learning, for today's session. But before we go into the main topic, let me just take a couple minutes to introduce myself and say how we got there. So my name is Elyes Manai. I'm the happy little fellow on the left, and I'm currently a machine learning consultant, a tech educator, and a Google developer expert in machine learning. And my expertise, not expertise, my specialty, let's say, or my experience with machine learning is actually quite diversified, as I have collaborated with a lot of entities which are from different backgrounds, meaning that I worked with startups, scale-ups, research labs, professors, communities, content creators, advocates, engineers, data scientists, etc., and business leaders. And I managed to get a 360 view of the AI field, let's say at least in the local market and the regional market, which is in the MENA region. And from there, I found out that there's a lot of progress happening in the AI field. And as progress goes on and on, the main issue isn't in the modeling part anymore, as we now have so many libraries that can do this very easily, and we even have auto machine learning libraries and tools that can do this for us. So the modeling isn't the issue anymore. But the issue is, how can you translate a real-world problem into something that AI can effectively solve? Not just solve, but effectively solve. And so in this case, there are many problems that occur that you never thought about when you first start your project, because the real world has so many outliers and out of distribution data points that you always have something new that you've never accounted for. And that is actually what we mean by robustness. So in our case, robustness is a way to make sure that our machine learning model, when it learned from the data, it learned, let's say, a general view, it learned enough points, enough diverse points, that it allows it to generalize even out of distribution. And at the very least, if it cannot perform at maximum capacity, at the very least, it will not make stupid mistakes, and we will therefore avoid critical errors in production. So that being said, let's just get right into it. So we need to first understand where exactly the problem of robustness occurs and why it's such a big, let's say it's such a big issue. And of course, we're going to see how we can solve it from the easiest ways to a bit more complicated ways. So let's get right into it. So let me first introduce the problem. You may have heard about these cases where AI goes wrong, as we say. And AI goes wrong in many cases. For example, in March 2018, Uber self-driving car did hit a bicyclist, but also in other occurrences hit pedestrians, and even some casualties were there. And in that case, they did not understand why it did. Although after that, they may know that there was a small problem with the distribution. In October 2018, a project Amazon wanted to do was an AI recruiter, by bias of resume, discriminated against women. And so they had to scratch that off. And then in a smart Chinese traffic camera in May 2019 gave a ticket to a man because he was scratching his face. But the way he scratched his face was resemblant of someone holding a phone, which is illegal while driving a car. So why does this happen? Why did the AI go wrong in all of these cases? Well, that's exactly what we want to know, actually, because sometimes it's not obvious why they did that wrong. We may have gotten a lot of data. We made our best to get the best neural architecture. We did our best for training, and yet something like this do happen. So to understand why this occurs at the very most basic level, let's go back to how machine learning works, or how an AI learns. Of course, I'm going to talk about the machine learning part, not on heuristics. So we're going to go in data-based modeling. So let's get a small, very simple example. Let's say we want to make a Spiderman classified, as simple as that, for our kids, for example. So in this case, we would reach out and scrap and collect lots of pictures of Spider-Man and try to make a model out of this data. But then something happens, and you get this data point. And in this case, maybe it will not classify it as Spider-Man because it has never seen a black Spider-Man before. They only know that the trademark is red and blue and some logo of a spider, but in this case it's all in reversed or it's black and white. So in this case, the model might not be able to tell that it was really a Spider-Man, or at least the confidence score won't be that higher up. Or I can give you another example. If I give you a comic book Spider-Man with flashier colors and let's say more acrobatic movements, maybe in that case also it will not be able to differentiate. So in this case, which is the first type of machine learning robustness, it's simply having enough diverse data points. So you want your model to be able to have seen, many different data points that will allow it to generalize better by having seen many different cases. And in this case, the simplest solution is just to do data augmentation or better data collection. It's as simple as that. And data augmentation, for those who do not know, is, I doubt someone doesn't know about it, but it's simply a way to have more data, let's say, in the quantity side. So you might make some rotation, some cropping, or get even more data and do some rotations, color shift, etc. So that's one way of doing this. But you already know that data augmentation isn't something new. But then I could go, let's say, go even further. And even if you train on those data points, now I can give you a example of a plush toy, not plush toy, but a figurine. So there are some differences in this case. But I can also go in and give you a mix. Now we have a black Spider-Man, which is also a comic book. And then we have Spider-Man without his mask. And I could go on and on and on. And so in this case, we are still in the augmentation part. There's no problem. We just need to scrap more data and get more data from each of these new points. But then I can go even further, which is, all right, what if now we have Spider-Man showing his back? We've never seen his back before. Or what if it's a long shot? What if it's a shot from way behind, and Spider-Man in this case is not easily observable. The features are not that easy to discern. So the thing is, where I want to go with this is that data augmentation is one of the easiest techniques, let's say, to tackle robustness, in the way that you just need to at each time add more diverse data points, something that you have never seen, etc., etc. And so it's a very good, actually, solution for production. The thing is that depending on your use case, you may not have the possibility to always be able to get more data. That's one of the problems with data collection and data augmentation, because data collection, in this case, it's easy. You just need to scrub the web for more pictures. But if you are in the medical field, for example, or you are in a defense or in a military, or even in finance, or any use case where data is either scarce or private or difficult to get, well, in that case, data collection may not be easy to do, and data augmentation might not be able to add a lot of worth, because most of data augmentation, what it does is it creates some sample points that are similar to the distribution we already have. But if you want to be robust, we wanted to be able to see distribution that it does not have, instead of reinforcing what you already have, which can lead to overfitting in that case. So a main takeout of this is that for tackling robustness, first, we need quality data collection processes. We need processes for data collection. It's not just scrapping everything we find. We need to find a way to be able to measure how good, how much of good quality our data currently is, and how we can collect it. And then we need to have better augmentation techniques beyond the simple zooming in, out, cropping, shifting. That is beyond simple copy and change of the same features. For example, some research has been going on using GANs to change colors, for example, of outfits, or to add some fixes. It's not that quality yet, but we will get there. But this is what we could make some custom augmentation techniques to add that part if we don't have it. But then the cons, the handicaps, as always, is that more data is not always possible, and you can't only trust data augmentation. And I'm going to tell you exactly what I mean with we can't only trust data augmentation. Let me give you an example. Let's say that you did manage to get a lot of data. Well, the thing is, more data might not help discern the features. Let me give you an example. Let's say that you've added a lot of Spider-Man pictures, and now it's really good at discerning Spider-Man. Now, for example, it can discern Spider-Man even from a distance, right? If I give you this picture now of my friend who has a Spider-Man mask, will it classify this picture as Spider-Man or as person wearing Spider-Man mask? Well, in that case, it might as well say that is Spider-Man, which is not true, because that's not Spider-Man, that's a person wearing a Spider-Man mask. Depending, again, on your use case, this might not be a problem. For example, if you are a toy company or any service company and you want to make a model that allows you to detect the logos, the games, anything that you are developing, and you want to see how many people are posting about it, where it's showing on social media. In that case, yes, this might be interesting to have something that can discern a class wherever it is. So that might be good. But if you are actually going to make a Spider-Man classifier, if I'm in that universe and I want to do that, or I'm trying to make, for example, a movie detector, for example, show how many seconds Spider-Man was in a movie. In that case, this cannot work. We need to find the actual Spider-Man. And then there are lookalikes. So there are cases where some characters look alike. For example, Deadpool and a Spider-Man actually are not that different. They have red and black colors in the same spots. They have white eyes. They have the same physique. Well, you might discern Deadpool by the color tone and the swords, but it's not that much of a difference, because in machine learning we actually don't work that much with colors. We do that in data augmentation. Anyways, so basically, just adding data might not help, because you are adding more data of the same distribution, and even if you try to make it diverse, well, you might have use cases, or you might have let's say examples like this that will always be a problem. So what can we do in this case? Well, in this case, we should go less from data and more into the modeling part. This example is one of the popular fooling and AI network examples, where we take pictures that look alike. For example, on the left, we have pictures of croissant and cats. In the middle, brownies and dogs. And on the right, owls and apples. And as you can see, they do look alike, and sometimes it's very difficult to discern between them, at the very least for the cat or croissant. In this case, adding more data might not be that helpful. We need to go more into the features and more into the modeling. We need to find a way to get better features, representations, or feature learning from the data. And so it's not anymore. So in the modeling phase, it's not in the input layer anymore. We're not working on the data part. We now need to work on the modeling part, so the hidden layers. How can you make it so that our model in the hidden layers can learn the best features possible from that data? So even if it's this lookalike, well, it can manage to discern between them. And so in this space, we are talking about feature representation, feature learning, etc., which is applicable in any situation. For images, we have the convolutions. For NLP, we have embeddings. And for sound, we have the spectrograms and the waves. So being able to get better representations so that the task itself, classification detection, gets done better. So in this case, we have also a couple of things we can do. So first of all, you might be interested by first choosing an effective architecture, and I can't stress this enough. With all the research and all the open source projects and all the use cases and all the projects, there are tons of architectures that are now specific to certain tasks. For example, if I'm in medical and biomedical sphere, these architectures on the right are models used for biomedical applications actually. And if I want to, for example, work on 3D, let's say 2D or 3D segmentation and medical imaging, well, UNet is one of the best architectures for that, proven by research, of course. And so we have to first start by choosing the most effective architecture that can allow us to elaborate and get the best features. And this might seem easy at first, but it does need a lot of experimenting and trying out things so that you can get something good, and it's not that easy actually. But then, even if you find one of the best architectures, let's say you find a battery or list of architectures you want to try, maybe there's still a problem. Maybe the model is not yet fine-tuned enough for your own problem, because in this case you are getting pre-trained maybe pre-trained models, maybe just architectures. In both cases, maybe it's still not enough for your own specific data set. And so what you're gonna do is simple transfer learning. So you're gonna add some layers and try to do the fine-tuning part. And in that case, if that does not work with some simple softmax layer, well, you might need to add some regularization layers. Now, one of those regularization layers you already know is dropout. And what dropout does, just briefly for those who don't know, is that instead of having all the layers, instead of having all the nodes and the layers touching each other and flowing the information past everyone, we selectively drop random nodes, random passages of the network so that it learns to generalize from all of the nodes. Instead of like finding a specific passage in the neural network that allows it to always get it right, we want to remove that overfitting, let's say, or that shortcut, so that the model in itself can generalize well within or given any data point, given any type of input. And so dropout is one of these regulation layers that allow us to do this and allow us to oblige the model to get better features in our case. And sometimes even that does not work. So we might need to go even further. Or for example, it might work, it gives us good results, but there are still some granularities in the output by the class results, where there still are 2 to 3 classes that are still too resemblant, let's say, and thus the model still cannot discern between them. And in that case, we're talking about very small differences. And in that case, what you can do is add some penalties for the loss. So you might have heard about loss regularization, in which case, if you have the initial loss function or cost function is the simple ground truth, sum of ground truth minus the sum of the predictions, so the weights times the inputs. And this would be the cost function. All right, so ground truth, difference between ground truth and predictions. And if this cost, for example, it's good, it's 0 point something or 1 point something, and you wanted to get even less and less, well, we can add some regularization to the loss function in itself. And you may already have heard of these. One of them being called L1 regularization, which in this case just gets the same cost function and adds a simple parameter, which is basically the sum, the absolute value of the sum of the weights. And so the bigger the weights, the bigger the cost function. And this is that would be the problem, because the bigger the weights, basically, the more it's prone to finding shortcuts and thus overfitting. And we don't want to do that. We are specifically making dropout in this case so that it does not find a shortcut that is, which means what's the shortcut means? It just means that this, for example, node, so these weights for a specific input are always the highest, and so they dominate the rest of the nodes. And so in this case, it will always flow through this part. So we don't want that to happen. So we don't want all of our weights or some of our weights to be too big. And so we add the actual weight values to the cost function so that not only we have a good cost function, which is very low, also the weights are very low, meaning that it's distributed. And so we have learned generalizable features. And you can go even further and do this even stricter if you wanted to be very, very, very specific, which is the L2, which is the same thing. However, instead of having the absolute values, we have these squares. So this is even further down the strict path, and we regularize it even further to the finest of granularities. So these two parts, so these three parts, so finding the best architecture, adding the different ways of dropout, there are 4 to 5 ways of doing a dropout, and then regularization on the loss, and you can even do regularization on the specific layers itself. All of them will help us to have a better model that can generalize better and learn better features so that you can do better tasks. But then, of course, there's always like a handicap. So in this case, we would need ways to make the modeling more efficient and strong yet flexible feature learning / importance / representation allowing for generalization. So this is what this part does in the modeling part, which is the architecture search and regularization. And I'm sure there are other things, but we don't have the time to see everything. So we need this type of hacks, let's say, or tips. But the handicap is that it might become prone to overfitting on some kind of data. And we might have issues with out-of-distribution generalization. Now, this is one of the problems. It's that it's the out-of-distribution generalization. The part when I say overfitting, I don't mean overfitting on the train, validation, and test data set. Of course not. But you might imagine, you might think that all possible data points for some use case is this big, and all our test, training, validation data is maybe a sphere just in the left down corner of that. And so while it's not overfitting, it's generalizable on this sphere, for the total data points, we are technically overfitting to this part of the graph. So we have 3 other parts that are left untrained. So that's what I call out of distribution generalization. It's very good for that part. If all you have in production is that part, then you're good. But if you want to make it something that can be very generalizable, for example, autonomous vehicles, in that case, we still have issues with out of distribution generalization. So that's for the second part, for the features and modeling part. We still have, yeah, we're good on time. Oh, and I forgot to add, all right, just ignore this picture. I forgot to add an animation. What I want to say is that even if, now we're gonna go third part, is that even if we do data augmentation, data collection, and we train our model for very efficient feature engineering, well, there still might some problems that might occur, and that will drive data scientists crazy because it's not apparent. And this is what you call adversarial attacks or noise attacks. So what these attacks do, let me give you an example, is, for example, you have a picture of a panda, and the model says it's a panda with 57.7 confidence, but then we add a noise mask. We generate a noise, and that noise might be just small. It's like a 0.007 times noise matrix, and when you apply it on the actual picture, visually, you don't see the difference. But the model does not see it visually, as you already know. It sees the pixels, it sees the values inside of it, and that's how they manage to find patterns. So in this case, what happened is that the picture got manipulated in a way that, to us humans, we cannot discern it was manipulated. And this can cause a lot of problems. So in this case, the panda has become a gibbon. And if you can go even further, a duck can become a horse. A sound that says "How are you?" can become "Open the door." Yeah, let's just say here, "Open the door," and you can imagine the kind of things that we can, the kind of problems that we can that can occur from this, especially if there's hacking into one system that can happen, or simply if you have let's say critical let's say application, and somehow there's an error in the hardware, and there's some noise that gets in and you cannot see it, or maybe even though you might be scrapping for data, collecting data, and you might not know there's something like this happening. And something that happens even naturally, because the camera lens can change it. sometimes the camera quality, sometimes let's say the age of the data point, it does affect the pictures. And we can go even further because there's now something called one pixel attack, where they only change one pixel in the photo. And as you can see, for example, we have a white pixel in this ship, which became a car, white pixel in the horse that became a dog, a black pixel in the horse that became a frog, etc., etc. This works well on lower dimension pictures, but at the same time, it's still possible to achieve that. So even one pixel change can affect this, and this is actually the heart of robustness. So if a hacker manages to send something like this into an input stream, and then the model does something, because it's not just giving predictions, it's doing something for those predictions, well, it might affect the users, the clients, the developers, whoever is using that. So we might find some patterns in the noise that will allow people to make problems for other people. So this is something that we need to avoid. Well, the good thing is that there is a simple way to do this, which basically is to not only train your model on pure images, but also train it on noisy images. So you incorporate this problem into your training phase. As so from a bug, it becomes a feature. And the way to do this is actually very easy. And you have two ways. Let me go back to this modeling part. You can either do data augmentation with noising, so the input images will be augmented to have noisy copies of them, and then you train it. Or you can incorporate the noise in the layers by itself by adding, for example, a Gaussian noise layer between your hidden layers. And what this will do is it will noisify the weights, to noisify the outputs. And so it will never be able to learn it on a pure image, depending on what type of model you're using, or if it's pre-training from scratch, etc., etc. Either of these can work. The most important thing is that you add noise into your training, so that does not get fooled by that anymore. And this is even this is not only for image. There's also for text. For example, for text, we have something called random insertion, random switch, synonym replacement, random deletion. The XLM transformer model used to learn on gibberish. Actually, they took words and then they shuffled them, and it managed to learn the representation of text well. So noise can be added in whatever data you have. You just need to find the best way of adding it. So that's how we can do it with noise. All right. So for this part of noise, we need to find ways to make modeling more robust to noise, which for now we have Gaussian noise and data augmentation with noise that we can do for now, which is very effective, to be honest with you. But the handicaps, of course, the possible loss of information, because you're trying to get from pure noise, so the noise might win sometimes. There's always pros and cons, and you have to experiment with that. That's the problem with this. I think, yeah, we're still good on time. And then you might have seen that. And then let's say one of the biggest problems that we will have in the robustness is humans themselves. So humans are fascinating creatures that always find ways to fool systems. And doesn't matter how robust you think your system is, humans will always find a way to overcome it. And so, for example, a tweet, I've seen a tweet not long ago where they taped black, how do you call this? Where they tape, it's tape, yeah, it's tapes in French, something else. So they put a tape on the speed limit, and which looks exactly like this, and a Tesla got fooled by that. Instead of setting the speed limit at 35, they put the car put the speed limit at 85, and it got fooled by a simple tape that got added in the speed limit. And this is an actual thing that happened. It got tweeted. You can see it in Twitter. This actually happened, and it's that easy to fool machine learning models if they're not robust to the noise. And other use case would be this one, which comes from a research paper actually, but it's quite common in real life. We have a lot of stop signs or road signs in general, which have been vandalized which have been, let's say, damaged, which changed. And so this can also fool machine learning models, and they will go from stop to something else. And that's actually what they see in the paper. It's also that easy to fool an AI. Then we have an NLP, the teen slangs, for example. Slangs is a problem because the time it takes you to train a model on a certain type of text, by the time you finish, you find some new text coming out. And so each, let's say, each period of time, there's a new trend, there's new slang that comes out, and all of those are out of distribution data points. And in NLP, it's even more difficult because text gets created like every day, and we can have new additions every day, and it's quite impossible to get all of them, let's say, efficiently, because the training time for such big models that are very good is tremendous. And so you can't add text every day. And so slang or trends or something that gets added every day, those are also big problems, because a word can change meaning from day to day, and the model might not be, and let's say the model developers or the model itself cannot pick that. They will use a wrong word, a word in a wrong setting, etc., etc., and it maybe cause problems. It cannot keep up with it. And then there's also some examples like putting a sticker on a label. For example, in this case, we have a banana on the top and it says banana in the green. That's good. But then we add a sticker on the table, and now it's something else that I cannot read. A toaster. Yeah, now it sees it as a toaster somehow. Well, to be honest, it does look quite a bit like a toaster on the sticker. I can see the features that make up a toaster, so maybe we can cut it some slack. But then but then it will depend how they train the model. Maybe it would be, if it was a multi-label or a detection task, maybe it would be better. It depends on the use case. But I saw another example where they literally wrote iPod on a piece of paper, sticked it to an apple, and then the model went from Apple to iPod. Yeah, that kind of thing happens. And finally, we have this kind of fooling. Well, where all they need to do is put something that's not usually on a human to fool person detectors. And this is actually what I was talking about at the first with Spiderman, with all the different ways of doing Spiderman that may seem like silly, but now this is actually something that's happening. It's being used in protests to hide identities. It now can be used like that to hide security cameras, and it's that simple to fool them. Well, in this case, what should happen is we take that data point and we add it to our training. That is an outlier. We need to train our model not only on normal humans wearing normal clothes, but also on different kind of costumes and accessories that might not occur, and hope that the model learns the features that a human is not made up with with their clothes, let's say, or accessories. They made by the humanoid figure. Maybe that same model is not that good, but hey, I have no data to say that clean. So basically, the problem with humans is that they always find new ways to train the system, and so you can't always be you can't always have something that's performant. You always have some new issues going on. But that's where a proper strategy comes in. What I mean with proper strategy is we need to incorporate in the training, production, looping phase ways to get those outliers, discern the priorities, and add them into our data as to turn bugs into features each time. And one last part that you can add would be, oh yeah, so sorry, I need to say. So for the humans part, we need to take into account many things. For example, new trends, new laws, updates. So anything that can change the distribution that we've had, and we need to make, we have to take that into account and get the updates and the new versions. We need to take into account real world issues like vandalisms, trolls, decay on the classes that on the labels you want to work on, and even for geographical and cultural differences, because road signs in America may not be the same in Africa. The culture, so for what some words mean in Asia may not be the same in South America. colors, let's say even the input data in itself, quality, etc. It differs from place to place, from culture to culture, from age group to age group. And so we have to take all of that into account depending on our use case, of course. But then there's always handicaps, is that if we want to do that, we need big infrastructure that can handle all those model variations and all those versioning, which includes the cost and the maintenance of all of that. So that's a big handicap, actually. And of course, we have the management of the many different models, data sets, the version data, the data versioning, the machine learning models versioning, etc., etc. So while this might be one of the most effective ways to tackle all of these issues, it's also one of the most costly and demanding. So it's not for everyone. However, if you can do that, we can do something else. Is that we can work on trying to understand why our model, for example, misclassified the banana for a toaster, why they misclassified the human for a non-human with the drawing, why they classified the speed limit. So this is actually another field that I'm going to just present. I don't have the time to present it in depth, but it's something that that is its own field in AI, but that is very tightly integrated with robustness, because with this we can achieve this, and it's the explainability part. Explainability is another field of machine learning that works on trying to explain the decisions, the features, why I did this, why I did that. And if you manage to explain the decisions that our models made, well, in that case, we might understand what they are looking at, what the model is looking at, why it got so much importance for that. And from there, we can go back and solve or correct some input data or some parameters. And the way it does this, there's a lot of ways to do explainability. There are ways specific for computer vision and NLP. There's ways specific for tabular data. There are model agnostic ways like alignment chat that allows you to try it on basically any type of model. But we're not going to go in depth in this because this needs its own session. But just know that there are explainability, there are a field, or let's say a specialty that's called explainability, that tries to understand why a model has done that, and thus by learning what the model is actually looking at. And a very small example, so that I don't leave you with nothing, is occlusion sensitivity, the one in yellow right here. It's one of the simplest way we can do that. Basically, it takes pictures, and for each pictures, it puts some blocks at different places, and it predicts each time it does the inference. And what it does, it gives us a matrix of importance to that to then know what parts, what pictures, where what are the confidence scores for each pictures. And since we have the same block moving from place to place, we can understand which parts were heavily affected by the occlusion of the data, so by adding noise or by adding a block. And I give you a simple example of dog versus wolf classifier. As you can see, we have a dog on the left, we have a wolf on the right, we have the red and blue things. And basically what that means is that from the blue is 0, 1 is red is 1, and the more red it is, the more the confidence score was high in that case, or let's say the more it was affected by the occlusion. And in this case, you can see that the actual dog and the actual wolf are at blue, which is similar to 0, meaning that they did not have any, or let's say not much effect on the actual classification, and the hot zone was actually in the background. So it was in the grass, it was in the snow. And what this shows us is that our model is not classifying the animals in itself, but they are classifying the backgrounds. And this comes from an example where they took a lot of pictures from wolves, a lot of pictures from dogs, but the bias that they did not know about was that most wolf pictures were in snow environment, and most dog pictures were in a park environment. So the dogs mostly had green backgrounds, while the wolves mostly had white backgrounds. And in that case, the model learned that by just identifying the backgrounds, it can manage to get good results on this data set. And that's exactly why it's a problem, because you will get good results, but then when you add it in production, it fails miserably. And this explainability is an awesome tool that anyone needs to add to their workflow to avoid critical errors in production. But that's a whole other session, so I'm not going to focus on that now. All right, we still have 5 minutes, so let's make a small recap of this. An interesting, let's say, an efficient pipeline would be. So I'm just speculating. I'm just ranting. It's not scientific, but yeah, what should be done is that in the training phase, we need to have a well-put data collection strategy. We need a strategy for collecting the data. It's not just let's collect. It shouldn't be an extra. It needs to be well put. How are we going to collect the good, diverse data points needed for this use case? Then we need to put to give that into diverse data augmentation techniques, and at the same time know what data augmentation techniques to work. The defaults are good. You have 10 data augmentation techniques that we can always use, but sometimes they are not useful. So why should I create more copies and have a heavier data set if I can instead focus on getting more diversified data points? From there, I have to get a well-chosen architecture. In this case, research papers can help a lot because they do that. They try a lot of things. Industry also can help, but not all industrials show their secret sauce. So there's a trade-off there. But a well-chosen architecture for starters that makes sure it has noise, regularization, dropout, or if not, you add it yourself in the fine-tuning layers, which then goes to an analysis of results by class performance for the testing phase to see what classes were well modeled, what classes were not. Finally, if possible, apply explainability algorithm to see where the problem is, and then you go back and you have to do this again and again until you get a more robust machine learning problem. It might seem very difficult and time-consuming compared to what we usually do, but if you are working on a company, on a critical use case, this will allow you to avoid errors in the future, and thus not put your project or whatever it is in peril. And finally, for the production, you need to incorporate outlier or noise data collection strategies so that we can detect all these noise and all the outliers, and try to add them into our workflow as to turn them into new features or turn them into new data collection strategies. And finally, a more efficient retraining strategy so that we can know where to do this. In this case, I'm talking about if we have a model that is split into many countries and cultures, we would, for example, need to retrain only the model for this country because they have an update, but no need to retrain the model for this country because they do not. So this, in a nutshell, still have 2 minutes. So one last slide I want to show you is this. In the end, if we have a really good model that learned the best representation, then in that case, it should be able to tell me there is a face in this wood log, there's a dog in this mountain, there's Donald Trump in this meat steak, that's a bear as a sock, that's a dinosaur and not a human doing push-up, and that's a face and not a banana. So in this case, if we have a really robust machine learning model that learn the representations, it should be able to detect these things in other things like we humans do, because that's how we learn. We learn the rare representation. So this might be a measure of success, and it will be interesting if we can work on something like this, like a data set or a strategy to test something like this. I would love to work on something like that. So this is what should be done, and this concludes our session about robustness and avoiding critical errors in production. I tried to be quick because I still have 1 minute. So thank you so much for being with. Thank you for following to the end. And let's connect if you have anything. I will be in the Slack to answer questions. And I am always looking for new friends. You can send an email, or you can find me at these social media with that name. Thank you so much.